All right, so I want to assume that I have a metric D on a non-empty set X. And now I want to introduce a fun concept with you. So let's pick any positive real number. We'll call it epsilon. You can call it whatever you want. And let's pick a particular point in my set X. Well, then the open ball of radius epsilon and center C is defined as, it's written B sub epsilon of C, and it's defined as the set of X in X such that the distance between X and C is less than epsilon. And if we want to think about this under the Euclidean space in R2, here's my point C, and then I'm just quite literally saying everything that's within a radius epsilon of C. Okay, so let's do some examples of these. This picture that I just drew is the right mind picture to have, but you need to realize that not every metric space looks like this. There are some interesting examples of metric spaces where the balls are actually square or flat or who knows what. So let's see some of these. So let's think about the standard metric over the reals. We might want to ask ourselves, what is the ball of radius 1/2 centered at 1? It's always nice to write down the definition. This is the set of real numbers such that the distance between x and 1 is less than 1/2, right? That's the same thing as the set of real numbers x such that x minus 1, the absolute value of x minus 1, 1 minus x, whatever you want to write, this is less than 1/2. And now if we want to, we can draw this on the number line. And we say, well, I'm centering at 1, and I can go out to out to 3/2. I can go out 1/2 to 3/2, or I can go down 1/2 to 1/2. And gosh, that's the open ball right there. And so this open ball is actually just the open interval 1/2 to 3/2. And I could do other examples, but the point is that flat interval is actually an open ball by our definition. So these aren't always geometric. These are based on our definition. So now let's look at another example. Let's think about this set, just A, B, C, D. And I want D to be the discrete metric. Keep in mind the discrete metric is a great metric, by the way, because the distance is either 0 or 1. If A and B are different, then the distance between them is 1. If A and B are the same, the distance between them is 0. And so we want to, maybe we should write a few of those down, like the distance between A and B is 1, the distance between B and C is 1, the distance between A and A is 0, so on and so forth. Okay, I'm going to erase those, but hopefully that was helpful. Let's write down a couple of these open balls. So what's the open ball of radius 1/2 centered at A? Well, by definition, it's the set of elements little x in our set big X such that the distance between A and X is less than 1/2, right? And so we think about it and we say, well, gosh, my distances are either 0 or 1. There's only one point in my space whose distance from A is less than 1/2, and that's A itself. Its distance between A and A is 0, so this is just the set A. Any other point is going to have distance 1, which is not less than 1/2. So here, the open ball of radius 1/2 is actually A. Let's think about the open ball of radius 1. Well, it's very similar. It's the set of points x and x such that the distance between A and x is less than 1. Same exact argument, right? The distance between A and x is either 1 itself, which is not less than 1, or 0. And so the only time you have distance less than 1 is when the distance is 0, which means you're A. So this is, which means x is A. So this is the set A again. And finally, you can pick any real number bigger than 1. And by any real number, I really do mean things like pi, right? If you scroll up to our definition, we said that this epsilon is any real number. So I can talk about the ball of radius pi centered at A. Let's write it down. This is the set of x and x such that The distance between A and X, I've switched the order here. I typically write X and A, but you realize they're the same thing, right? It doesn't matter. The distance between A and X, I want this to be less than pi. And now you say, well, geez, everything in X has, every little x has distance less than pi from A because the distance is either 0 or 1. So this is actually the entire space X. It's everything. So the discrete metric is kind of fun. It's very different. And again, these are all open balls, even though they don't look round at all. They're just sets of points. Let's go back now. Maybe we should do a formal example with Euclidean space in R2 since I've been alluding to that. So I've already got it written down. Let's erase that and we'll scroll down and I'll deal with the spacing here. I'll scoot it up. All right. So let's think about the Euclidean metric on R2. This is just your standard notion of distance on the reals. And so I can, for example, talk about the ball of radius 1 centered at the point 0, 0. Well, this open ball actually looks like an open ball. It's centered at 0, 0, and it has radius 1. This is just the open unit circle, and it's everything in between, by the way, as well. And again, you can talk about the open ball of radius 2 centered at the point 2, 1. I'm putting extra parentheses because it's centered at that point in my space. The point is 2, 1. And so again, this is just very, very elementary. You would go over to what? X is 1, 2, Y is 1, and then you want to have radius 2. So something like this. I don't know if I guess I'll do all of it. 1, 2. And you would have, whoops, it needs to be open, so I can't use my thing, but it would have something looking like that. And so that's the open ball of radius 2 sitting at the point 2, 1. All right, well, what do open balls look like under the Chebyshev metric on R2? So let's think about it. Let's erase this. And let's just think about the open ball of radius 1 at the point 0, 0. So we'll try to sketch it over here. Let's see. Okay, so let's remind ourselves how the distance works. So the distance between x1, x2, and y1, y2 is the max of absolute value x1 minus y1, and then x2 minus y2. So let's try and figure out some points that have distance 1 from 0. I claim that 0, 1, I'm going to put that up here. We're going to make that length 1. This has distance 1 from 0, 0. Right? I'm centering this thing at the origin. And the reason is that if I look at the distance between 0, 0 and 0, 1, then when I take max of, this is going to be the absolute value of 0, which is 0, and the absolute value of negative 1, which is 1, so that's exactly 1. And then what I want you to realize is actually you can go and do the same thing down as well. So that point are all on my boundary. And I can go over here when x is 1 and y is 0, when x is minus 1 and y is 0. And it turns out that this open ball looks like this. You actually do get a square. And that's what it looks like. Oops, I want to go up this way. And we'll erase that guy. And so don't let anybody tell you that there's no such thing as a square circle, because I just drew one. That, by definition, is a open ball. If you define the circle as the set of all points equal distance from a fixed point, that's exactly what the boundary is. And so we're going to call that an open ball, even though it looks like a square. And the point is, anything inside of this is distance 1 away from the center. So your notion of distance in R2 has typically been circular. You pick a point and you go and you draw the line between them. Here, the distance between this point and the origin is not square root of 2. You would think of it as square root of 2, right? You would come and say, well, distance is root 2. This distance right here is actually exactly 1. These are distance 1 away. So kind of fun. All right, so let's stop